Okay, so let us start capacitance. This chapter capacitance we will start. That is in your Friday exam portion. Okay, so capacitance, what is capacitance? Let us write it. It is the property, it is the property of a conductor by which it can store charges. Okay, it can store charges. So the charge storing property is called capacitance. Suppose there is a conductor, and to this conductor you are giving some charges. Let us say that you have given some charges. Okay, some charges, and you know the charge will spread over its surface like this. Like this, charges will spread, and we have studied last class these properties of conductors and all that. So charges will spread over its surface. So it will develop a constant potential. We have also studied that its potential will be constant. Okay. So now one important thing is that how do we measure the this charge storage capacity, right? How can we measure the charge storage capacity? What do you think? How to measure that? Hmm? Because you are giving charge, so it is getting a voltage. You give more charge, it will develop more voltage. You give more charge, it will develop more voltage. So how to decide this? So we can decide this by the ratio of q by v. Q by v. So you give charge and it will develop a constant voltage. You give more charge, it will develop more. So this ratio is going to be constant. That is what is called capacitance. Okay. So this is how we are defining capacitance of a conductor. This is capacitance of a conductor, of an isolated conductor. Isolated conductor. So this is an isolated, means this is a one single single conductor, and if you are giving more charges, its voltage is also changing. But for a given charge, it will have a constant voltage. So the ratio of charge to voltage, that is called capacitance. Now you can also define capacitance as capacitance. Capacitance is the ratio of is the is the charge stored is the charge stored per unit voltage developed correct. So if you give some charge, suppose for example keep the voltage 1, and you have given some charge for which voltage has become 1, then that charge will become equal to capacitance. Per unit voltage, what is the charge it can store? So if you give more voltage, it will store more charges, right? That is the idea behind it. And what is the unit of this? Unit, SI unit of capacitance is 1 farad. 1 farad, not Faraday, it is farad. Okay, 1 farad. And 1 farad is a large unit. Note that this 1 farad is a large unit. Large unit. Okay. So that is why practical unit is 1 microfarad, 1 nanofarad, 1 picofarad. Okay. So these will be practical units because 1 farad is very large number. So we do not generally use that. Okay. So let us now understand further about this capacitance, how to calculate capacitance. Let us take a sphere. Okay. A spherical conductor. Suppose this is a spherical conductor and you give some charge, so it will develop some charge. Note that this spherical conductor can be either solid or hollow. Hollow means it is like a cell. So it can be anything and its radius is r, because charge will store only on the surface. Now the thing is that, tell me what is the formula for potential. You have studied potential formula. Tell me potential of this. Yes. What will be the potential of this? Yes, Satres. Potential formula. Huh? Yes, correct. K Q by R. K Q by R. Okay, so what is capacitance then? Capacitance is the ratio of what? Capacitance is ratio of charge by voltage. So do that. Voltage we know already. So substitute voltage. So this is KQ by R, right? So QQ will get cancelled. So capacitance will come as R by K. K is 1 by 4 pi epsilon naught. So it will become 4 pi epsilon naught R. This is the capacitance of a single one spherical capacitor. Sphere can be solid or hollow, it doesn't matter. Okay, this is what it is. Now, if you try to calculate the, suppose for example, this is Earth. Let us say this sphere is the Earth. What will be its capacitance? Calculate 4 pi epsilon naught into R. Radius of Earth is how much? You know what is radius of Earth? Yes, 6400 kilometer means 10 to the power 3. Keep SI unit. Calculate. This is 4 pi now. 1 by 4 pi epsilon naught is 9 into 10 to the power 9. So it will become 1 by 9 into 10 to the power 9. Right. So calculate how much this will come. Will it come 711? Just check that. 711 microfarad will come. You check this. Right. 711 microfarad. Because this is farad. Okay. This is farad. This farad we are converting into microfarad. So it's, so that means the entire earth, entire earth has only this much capacitance, which is so small, right? That is why we say that farad is a very large quantity. Okay, let us move next. Now let's understand very carefully some technique we are going to develop. Because of that spherical capacitor you will be trying to calculate. Okay, so let us first take sphere, because the sphere is so symmetric. Okay, let us try to understand what is spherical capacitor. So now, just now we have studied this spherical capacitor. Let's try to understand little bit more concept about it. So this is the capacitor of radius r. Okay, and you have given a charge on this Q. So let us say this charge has got positive charge, got spread here. But now the question is, from where have this charge come? From where this charge has come? You might have got it from somewhere. From very, very large distance you have brought this charge. Large distance means you have brought from infinity. This charge you have brought from infinity. And you know the entire system or the entire universe is neutral. Entire universe is neutral. There is no charge. So if you pick any charge from somewhere, they will get opposite charge developed. So if you are bringing this charge q from infinity, so infinity has got a negative charge, correct? Right, because entire universe is zero charge. So you are bringing this charge from here, so there this become minus q, this has become plus q. Okay, so you may think now, you can understand that Actually there are two spheres. We were seeing only one sphere actually, but there are two spheres. One sphere is having infinite radius, because you can make a sphere of infinite radius from where you are bringing the charge. Okay, so this capacitance which we have studied right now is nothing but, we have seen capacitance as charge by voltage, but actually it is nothing but, let us say this point has potential v1 and this charge has, this sphere has potential v2. So the charge divided by it is potential difference basically, right? Potential difference is basically v1 minus v2 here. Potential difference is of course always magnitude, whether potential difference is always big minus small, it is not small minus big. Even if it is coming negative, you take magnitude. Okay, so note that this v2 is 0 because this is infinity. You know that potential at infinity is taken as 0, right? Okay, so potential at infinity is taken as 0, that is why v2 is 0. It is not going to make any difference, it will be just v1 only because this is 0. So all calculation are going to give the same result which we derived, that is means it is 4 pi epsilon naught r. That is what it is. This is what. So correct. So this formula for 4 pi epsilon naught capacitor, when we are saying of a sphere, it is with relation of a sphere at infinity, which has opposite charges. Okay, this is the idea. Now let us try to understand how to calculate. Also know that while we are calculating this can be also derived from a very fundamental approach. What is that fundamental approach? Fundamental approach is that suppose I take any point here in between here, and I know that electric field due to this, it is going like this electric field lines. So if I move, let us say if I move a distance in the direction of electric field, a distance of dr, so there is a change of potential, right? Dv. So we know this formula that dv is equal to minus e dr or e dot dr, right? We know this, very fundamental, because you can calculate dv using this formula. So you can integrate then. So this will be change of potential. This is change of potential. Okay, minus electric field formula is kq by r square dr, and you are going from the surface to infinity. So capital R to infinity you can go. So you are going change of potential. So final potential at infinity 0. Here potential is v1. Okay, or this is potential difference. If you don't want to calculate that, you calculate the difference of potential. So minus, and then it become plus kq by r, right? And this r you have to take from capital R to infinity. So when you take 1 by infinity, that becomes 0. So minus kq by capital R. This is the change of potential. Note that what you have calculated is change of potential while going from here to there. So but here potential is 0, right? So basically this is 0 minus potential of that surface. So you will get kq by r only. But the idea is that we can take magnitude of this, right? And we can still calculate that same answer will come. So this is the approach of calculating capacitance. Now let us take two sphere, means two spherical cell, and try to apply the same approach. But there is another different approach also. Whichever is easier, you apply that. Okay? Whichever easier it looks like, you apply that. Suppose this is one capacitor of radius A and another capacitor of radius B. Okay, and let us say that in this we have charge. We have charge here. We have charge Q1 or plus Q, and here charge is minus Q. So this charge is minus Q. Okay, capacitor at infinity is also there, but now you have to study the interaction between that two. So infinity is very far away, so their interaction you can leave it. So that means this point have potential V1, this point have potential V2. So how can we define capacitance? Capacitance will be defined as charge by potential difference. Here potential difference means difference of V1, V2, right? Okay, so let us calculate V1. Now we will just use formula to calculate V1 and V2 without doing integration. Integration also you can do it, but let us do a very simple method. Tell me how to write the potential of point 1. This potential 1, how can we write it? So first you learn like this method. Potential of this point potential will be written as potential of that point due to that same surface V11 and potential of 1 due to the outer surface. Okay. Similarly here V2 also you will write the same manner. We'll write this afterward. First let us calculate this. So potential of here, it's due to on surface is kq by a, kq by its radius is a. Now potential here due to this, and this point is inside, this point is inside. So for inside point it is k cube by that radius of bigger one. So k, its charge is minus q and that radius is b. Correct? This is v1. Same way tell me v2. v2 v2 also same manner. v2 we will write as v at 2 due to 1 and v at 2 due to 2 itself. So at this point, if you are looking here, so this will create potential and this surface will also create potential. So due to this point is outside, so this point, this is going to behave like a point charge. So k q by b plus, now due to its own charge, so k minus q by its own radius. That's all. That's all we have got. Did you understand this v1 v2? Okay, now take the difference. Definitely, which is bigger? Can you guess which is bigger? Which is higher voltage? V1 higher voltage, because this term is same and here smaller radius is there, so larger it is. So V1 minus V2 is going to be change of potential is equal to, subtract that, this get cancelled. KQ you can take common, 1 by A minus 1 by B. So now what we want? We want to calculate capacitance of the system as charge by potential difference. So charge by potential difference is substitute kq, 1 by A minus 1 by B. So k will become, qq got cancelled, k become here 4 pi epsilon naught. LCM you take, so AB by B minus A. Clear? So this is the formula for capacitance. This is the formula for capacitance of a spherical capacitor. Now this is called spherical capacitor. Spherical capacitor, because it is now a device which is going to store charge. Previously it was just a single sphere which was like a isolated conductor, but now this is two conductors. It is made up of two conductors and they are storing equal and opposite charges. Okay, so these type of devices are called capacitors. So for a spherical capacitor, this formula is there. We can prove it this way, or by integration also you can prove. You have to take electric field here and then integrate, you will get the same answer, right? That's capacitor. Okay, now try to understand little bit more in this. Some technique we will use now. Suppose that there is a two spherical capacitor, means it's a spherical capacitor, and they are saying that the inner sphere, inner one is earth, right? Inner one is going to be earth. Earth means its voltage will become 0 volt. Okay, 0 volt. And outer one has been given some charge q. So, and let's say this radius is a and outer radius is b. Okay, so what is the capacitance of this system? Okay, what is the capacitance of this system? So let us say that here some charges is small q is there, plus q, here will be minus q, and remaining charge will be there here. Correct? Charge distribution. So here due to induction this can happen, and note that connecting with ground means its voltage has become 0, its charge will not become 0, its voltage becomes 0, right? Okay, so let us say then outer surface some small q is charge, so opposite induction happen, So minus q will be there, but total charge on this is capital Q. So this must be q plus q, so that small q will get cancelled, it will be capital Q due to charge conservation. Now how to calculate this capacitance of this system? Hmm? How to calculate? Now you need to consider this outer charge. Why? Because here this may be interacting with the outer, means interacting with the infinity, because this q plus q will also induce some charge at infinity. Suppose you are taking a sphere of infinite radius. Okay, suppose I take a sphere of infinite radius. So you can also now consider the effect of induction here. Opposite charges you can induce. Okay, on this. This is a spherical cell which is of infinite radius, and now we can consider induction effect between them. So that means now here you need to take previously note that while we derive this one, why did we not consider infinite radius at infinity? The reason is that what is the reason? The reason is that here we have taken a plus charge q, plus capital Q minus capital Q, and we are not considering any charge here, 0. Here we are taking 0 charge this side. Okay, so because outer surface is having 0 charge, so infinity, even if you consider a sphere at infinity, you have to take 0 charge only. So there is no interaction between them. Understanding? Yes. So that is why here we have not considered while doing it, but here now we have to consider in this case, because outer surface has some charge. Okay, so how to do the calculation here? And note that this point, this here, this voltage is also 0. This voltage is also 0. Okay, so this voltage is 0 and that voltage is also 0, but its voltage is not 0. Let us write this is V1 which is 0, V2 which is not 0, but V3 is 0, like this. Okay. Right. How to calculate the capacitance of this system? We'll keep this question right now. We'll see the solution after, but I hope you have understood this diagram. Yes. Similarly, I will come to this page afterwards. Similarly, another case also I will take and I will draw the diagram. Now, this case we are considering this sphere and this is sphere, and here this time we are going to ground this one. This you ground and give some charge capital Q here. Okay. So if you are giving plus Q, the internal surface will have minus Q. Minus Q will be there here, and outer surface here, how much charge it will have. Let us say, if you don't know, let us write some q. Here also you may consider a sphere at very big. Okay, so here radiuses you will can take this radius as a, this radius you can take b, and this largest radius you can take infinity, this one. Okay, so interaction you can consider, but first of all you should know whether this q will exist or not. Okay, because q, small q may become 0 here, because you know this system is just like the first case. You remember first case, right? First case was like that. So we will see that, but one thing is sure, that here v1 will be there and this voltage v1 will be there, v2 will be 0 and v3 will be 0. How to calculate capacitance of this? So there are two cases we have two cases. What are those two cases? First case, case 1 is concentric cells, spherical cells, concentric spherical cells. We have concentric, two cells are there. Infinity you leave it. Two cells are there, and which one is earth? Inner is earth. Inner is earthed, and outer is charged. Outer is charged. This is the condition. We have two concentric cell, inner one is earth, outer is charged. What is the combination capacitance of this? And second case is that, second case 2, this is also concentric cells, right? This is also concentric cells. In this concentric cells, outer is earth, outer one is earth, and inner one is charged. Inner one is charged. Okay, so inner one is given charge, outer one is earth. Are you clear about this? So these two cases derivation we will come after, once we understand little bit about circuit diagram. But here one calculation you can definitely do, particularly in this case. You know this voltage will be 0, that you know. So you will be able to find the small q here. Let us write voltage V2. Same approach, write the voltage V2. So voltage V2 will be 2 due to 1 plus 2 due to 2, correct? Right. So, and that infinity interaction, that voltage, that charge will not create, because that charge is very, very far away. Okay, very, very far away. So right now leave. So V21 you calculate, and V2 has to be 0. So I'm equating this to 0. So V21 means due to this one, how much it will create here, potential. This charge is capital Q. So K capital Q by this distance, which will be B, plus now due to its own surface. So K, this charge is small q, and this charge is how much? This charge, total charge will be how much? Minus q plus small q. So minus capital Q plus small q, right? That is total charge. So its own surface. So K cube by its radius B. Now tell me what will be Q, because this will be going 0. Capital K is this minus will cancel out. So you will definitely find that small q is coming 0. Yes, small q is coming 0. That means in this case, this charge is not at all there. So that is why this surface is having no interaction with that. Forget about that. Okay. So that means this case has become exactly like the first case now, right? Exactly like a first case it has become. That's all. So that means here you can just write the formula. Now you don't have to worry about this. This case you write the formula. Initially what we have derived, that two capacitor. So capacitance will be 4 pi epsilon naught AB by B minus A. This is the formula for this case. But when you have earth, the inner cell, when you have earth, this case we have to wait. We will come, because this is interacting here, some charges are there, it will interact with this. So there is a different way to calculate that. We'll come to that. Okay, now let us go to parallel plate capacitor and try to understand some concept related with that. Parallel plate capacitor. Parallel plate capacitors. So what are capacitors? Capacitors are device to store charge. Device to store charge. So we have just now seen spherical capacitors. So there are basically three types of capacitors. Spherical capacitors, where there are concentric spherical cells, and there are parallel plate capacitors, where there are two parallel plates. Like one plate, you can see like this, one plate, and there is another plate. Two plate facing each other, they will be facing each other, and you can give on one plate charge plus q, another charge minus q. They will store charges like that, just like in spherical cells, one cell was plus, another cell was minus, same amount of charge or plus minus. So this type of arrangement is called parallel plate. That means two plates are parallel to each other. Now the shape of this need not be square or rectangle, it can be circular plates also, like this. Okay, but definitely their areas will be equal only. So you have to give plus q and minus q, their areas will be equal. But suppose if areas are not equal, then for example, suppose I take this, let's say I take a small rectangle, and I take a big rectangle. Then here what will happen is that this, suppose you have given some charge plus q on this, and if you give a minus q charge on this, so what happen, these charges will be present here, and this charge will try to bring all the negative charge only here only. All the negative charge will happen, it will come in this region only. This is what we have to note. All these negative charges minus q will come just in front of this, although you have kept a larger area, but this area there will be no interaction because nothing is in front of this, right? Clear? So you need to understand this, that the area only where a common area of interaction you have to take. This is a small, this is big, so smaller area you take, because smaller area is common area. Whatever is common area, that only you have to take. Okay. Generally the areas are equal. Okay. So now let us study parallel plate capacitor in detail. So parallel plate capacitor are like two plates. Now these two plates I will represent like this, flat like line, because when you see from front it will look like this. So it has plus q charge and it has minus q charge, and the charges are on the inner surface because of induction. Let's say the distance between them is d, and the area of the plate, because plate will be like this, so it will have some area, cross section area, same cross section area. How to calculate capacitance of this? So again you need to calculate the potential difference. So here direct formula you can use, potential difference is equal to minus change of potential, but let us write potential difference. So minus sign I will not write. Electric field is going to be uniform, you know that. Can you tell me what is the value of electric field inside these two plates? Yes. What is electric field inside these two plates? Forgotten? Hmm. No, no, sigma by 2 epsilon naught is due to one plate only, na? Right? Due to this one is sigma by 2 epsilon naught. But there is a negative charge plate also. This negative charge plate also creates the field in the same direction, sigma by 2 epsilon naught. So both the field will add up, right? Yes. So total will be sigma by 2 epsilon naught plus sigma by 2 epsilon naught. So we will have sigma by epsilon naught. This is the field inside the capacitor. And note that this set field is not there, because positive this field and this field will cancel out. Here also field is not there. So outside the parallel plate capacitor, fields are zero. Only field is present in between that. Now we will apply this, and distance is d, so field into the distance d, this is the potential difference. So let us calculate. So this field is sigma by epsilon naught into the distance d, sigma is charge by area. So this is how we are getting capacitance. Capacitance is q by delta v. Delta v you substitute, q a epsilon naught into d, q get cancelled, epsilon naught a by d. This is the capacitance of a parallel plate capacitor. Are you clear about this? Capacitance of a parallel plate capacitor. So it depends on what? Epsilon naught, because we have taken vacuum. If there is a medium, so it will become k times epsilon naught. K will be dielectric constant. Area and so on what factors capacitance depends? On what factors? So capacitance depends on C depends on first medium, second dimensions, that's all. Dimension. Note that this capacitance does not depend on charge and voltage. So C does not depend C does not depend on charge and potential difference. But then C is the ratio of charge and potential difference. Yes, that is correct. C is the ratio of charge and potential difference, but it does not depend, because if you increase Q, delta V will increase, the ratio will remain constant. Clear? Okay, so that is what is parallel plate capacitor. Now, what else in parallel plate capacitor? Now, let us understand two important things before we go further. So, that is called voltage rule, and second is called charge rule, charge rule, voltage rule and charge rule. So, what is voltage rule? It is based on energy conservation. Based on energy conservation. And what is charge rule? It is based on charge conservation. Sometimes these two laws are also known as Kirchhoff's law. They are also called Kirchhoff's law. But let us not get bothered with this term Kirchhoff's law. You just note that these are called voltage rule and charge rule. Try to understand what it is. Suppose that there is a circuit where we have two capacitors connected with a battery. Battery has plus and minus, it has voltage V. This V is the voltage difference between the terminals of the battery, and here this will be sending, so capacitor will store some charge, right? So it will store plus q minus q plus q minus q, like that. So this positive end supplies a plus q to this side, and negative end supplies minus q to that side. Okay, so negative end will supply minus q to this plate, positive end will supply plus q to that plate. Okay, and this on the, now note that what about this plate? These plates are getting charged due to induction. These two plates are getting equal and opposite charges due to induction. They are not connected with battery, right? Okay, they are not connected with battery, they are getting charged. So if you see the sum of total charges on these two plates, they are zero because they are not connected with battery. These two plates are just getting charges due to induction from this side and due to that side. Okay, battery is supplying charges only to this plate and that plate. Okay, right. So what is voltage rule? Try to understand this voltage rule here. Suppose if you take the difference of the potential here and the difference of potential here, let us call this as I think better you can name this point. Let us name this point as point 1 and this side is point 2. Note that these two are connected to the same point 2, they will have same potential. This side is potential 3. Okay, so note that this point is 1, so all these points are 1 1 1 1 1 because nothing is connected here. All these points are 3 3 3 3 3 3 3 3 because nothing is connected. So when nothing is connected in between, it is same potential or same point. Okay, this you have to understand. Here, like this point is 2 2 2 2 2 2. All these points are 2 only because nothing is connected. First, we need to understand this. So there are basically 3 points here. Point 1, all these points are 1. These points are 2. These points are 3. Clear? Are you clear? Yeah. So these 3 points are there, and their potentials you can name as V1, V2, V3. So what is this V? This V is the difference. So what is this V? This V is the difference of V1 minus V2. V1 is higher potential because it is positive. This V3 is low. Sorry, not 2, V3, because that side is 3, na, right? That side is 3. So what is this? This V is the difference of V is the difference of these two potentials. That side is potential 3, this side potential 1. So V1 minus V3 because V1 is higher and V3 is lower. This is V. Now let us understand this. This we can write as V1 minus V2 plus V2 minus V3. Can we write it? because 2 will not matter now. This 2 will get cancelled, right? Correct. Now we have to understand this, that this V can be called as this V1 minus V2 is potential of this minus potential of this. Okay. Note that left side plate minus right side plate. Similarly here V2 minus V3 is potential of this left plate minus potential of right plate. You can call this as delta V1 and you can call this as delta V2. So now this is an important concept coming here, that the total potential difference which you have applied by the battery is equal to sum of this potential difference plus sum of this potential difference. Are you understanding? So this is what is called voltage law. In voltage law, this will happen. And note that these two capacitors are called series. They are connected in series. Series combination. Series combination. So in series combination, voltage law will happen. Voltage law, we have to follow voltage law in series combination. Okay. Similarly, what will happen in that case also we will see that. But more important point to note here in series is that charge also remains same. So note one point, that charge, same charge, same charge on each capacitor. So note that capacitor is a arrangement of two plates, right? Because it's a parallel plate capacitor. When we say, that means two plates are there. So two plates make one capacitor. Okay. So when we say charge, which charge are you talking about? Are you talking plus Q minus? No, we are taking the magnitude of charge. Okay. When we say charge means we are taking, because two capacitors are in series here, and you can see that they have plus, of course it can have plus Q plus Q minus, but this is one capacitor, this is another capacitor, and they have same amount of charge. Amount of charge is same. Clear? So this is what happens in series. In series, they will have same charge and voltage law will follow in series. Voltage law will follow. Okay. Are you clear about this? Yes. Then what happens in parallel? Now note what happens in parallel. Means what is charge rule? Charge rule will apply in parallel. Let us try to understand. So suppose if there is a two capacitor, parallel plate capacitor are connected like this, and it is connected with a battery. Now here you need to understand the important point. Suppose if I have taken potential difference is V, and let us say I have taken this point as 1. So note that all these points are going to be 1, 1, 1, 1, 1, 1, because nothing is connected till now here. That side we cannot take 1 because that is another side. So here you take this as 2, 2, 2, 2, 2, 2, 2. So that means there are only 2 points here. Are you understanding? There are only 2 points here. Now this V is nothing but the, because this is plus and this is minus, so V is the potential difference, which is V1 minus V2. That is what is potential difference. Okay, what about now charges? So this battery will be supplying some charge. As I told, this positive terminal will supply plus Q and negative terminal will supply minus Q. So minus Q will come from this side and plus Q. Now this plus Q which is coming has to break into two branches. There are two branches here. So let us say plus Q breaks into plus Q1 and plus Q2. Okay. So here Q2 will go, Q2 will go, and here Q1 will go. So this is happening because this branch is breaking. One single branch is breaking into two branches. Okay. So this is Q1 and Q2. Q1 is lower one and Q2 is upper. So same thing here also, because of induction will happen, right? So here minus Q2 will happen and here minus Q1 will happen. So you can also say that this minus Q which is coming is breaking into two parts, which is minus Q1 and minus Q2. Are you understanding this? This I have written opposite, I think. This will be 2 and that will be 1. This will be minus Q2 and this will be minus Q1. So this, just like symmetric, this is breaking lower as plus q1, here lower is minus q1, here upper is plus q2, here upper is minus q2, like that it is happening. This is called charge distribution. Now what is the charge rule? Charge rule is coming at the junction. Now you see, where is the charge dividing? Charge is dividing here, charge is dividing here, or charge is dividing here. Here negative charge is dividing here, yet positive charge is dividing. So wherever charges are getting divided into different branch, that point is called junction. Junction. So this is a junction, or you can say this is also a junction. So what does this junction rule is? Junction rule is that, or charge rule is, this charge which will be coming here, it will break into two parts. So the same charge is breaking now. We cannot say that some charge is getting created, right? Or charge is getting destroyed. Charge is not getting created, or charge is not getting destroyed. Same charge q is breaking. So you can say that this q is breaking as q1 plus q2. Or here you can say that this minus q is breaking into minus q1 plus minus q2. Clear? Are you understanding this? That is what it is. So these two important rules are very important. So this charge rule you will apply whenever they are parallel. And note that the potential difference across both the capacitor, suppose first capacitor is C1 and second is C2. So across both this capacitor, the same potential difference is V1 minus V2, here also V1 minus V2. So in parallel, you have to apply charge rule, right? Charge rule you have to apply, and you need to also apply what? You need to also apply what? Same potential on each capacitor. Same potential difference, same potential difference across each capacitor. Same potential difference across it. So this is the story about parallel. So in parallel, what we will do? In parallel, we will break the charge and apply charge conservation, and potentials we have to keep same. And in series, what we will do? In series, we will keep the same charge, plus minus, but we will divide the voltage. So total voltage of battery will divide into this and this. Okay. So now let us try to apply some concept here to get what is the equivalent capacitance. Okay, so because we can write V equal to V delta V1 delta V2, now let us write the capacitor formula. So you know capacitor means C is what? C is Q by potential difference, right? So you know that Q is equal to Q by C is what? C is equal to Q by potential difference. So potential difference can be written as charge by capacitance, right? Okay. So here in this series, you can take first capacitor as C1. Let us say that this capacitor is C1 and this capacitor is C2. Here also like that. Let us take this is C1 and this is C2. Try to use this idea here. So C1 will be what? C1 will be this Q divided by this voltage difference, and C2 will be this charge divided by voltage difference. So voltage difference will come as charge by capacitance. So this V can be written as this charge by capacitance 1 and this charge by capacitance 2, right? Delta V2 will come charged by capacitance 2, delta V1 will come charged by capacitance 1. Okay. So now I want to replace both this series, both this series I want to replace by a single capacitor, which is called C equivalent. Okay. Why we'll call C equivalent? Because if you connect a battery here, this will be battery will has given charge q, right? Plus q minus q, here also plus q minus q. Now I want to replace these two into a single one. Single means it is kept within the same battery. We are going to keep it. So this battery will also supply the same charge, right? It will supply q plus minus. So the story is same, only thing is that two capacitors are being replaced by one equivalent capacitance or capacitor. So now I can write the capacitance equivalent here also. Let us write this. How will you write this voltage? Because this voltage is same. So if you apply voltage of equivalent, you can write Q by C equivalent. Can we write this? So we can write this as Q by C equivalent is equal to Q by C1 plus Q by C2. So you will see that this Q1 will get cancelled here. So this formula will come 1 by C equivalent is 1 by C1 plus 1 by C2. So this is for parallel series. Parallel means what? Parallel means what will divide? I told parallel charge will divide Q1 plus Q2. So again same manner, these two parallel arrangement can be replaced by a single capacitor, right? So this charge can be written as C equivalent into voltage. Here Q1 will be C1 into V plus C2 into V, because here voltage difference remains same, right? Voltage difference remains same. So this will get cancelled. So here simple formula comes, C equivalent is C1 plus C2. Are you clear about this? Yes. So this is happening in parallel and this is happening in series. That's what it is. So I think these results are important. So now you can remember this result. So next class we will see further about that. We will see further more derivation, and then with spherical also will come back, and cylindrical capacitor also will derive further. Okay. Right? So meanwhile, you start working for your Monday exam. You target all the questions of potentials we have already covered, and you solve as many problems as possible. Right? Okay. Then we'll see next. Okay. Bye bye.